Our next speaker is Miquel Vidal from the University of Barcelona. He's here in person, and then we have Viktor Dück online. They have 25 minutes, and they will share the presentation. We have Viktor online. Is Viktor here? Can we hear you? Viktor? From the
Victor, do you hear us?
He's muted.
Victor is here.
He's muted.
No, let's go start and then see if Victor connects.
Okay.
Are you there, Victor?
You can start.
Okay, let's be starting. Thank you, Estela, and good afternoon to everyone. And the what I'm going to present to you, as we have mentioned, is part of the collaboration between the Helmholtz Zentrum Dresden-Rossendorf, and so Viktor and Fran Bock are co-authors of this presentation, and then the work by my team with Vidal, Dídac, and Joan, which are our PhD students. So, actually, as Estela was saying, you're going to have two presentations for the price of one, because we have split our contributions to this work into presentations. So, to put you in context, this work has been carried out within the task 2.7 that acknowledges the main role of KD as a relevant input data for many radiological risk assessment approaches. So the main aim of this task is to try to understand better the behavior of a number of naturally occurring radionuclides such as polonium, radium, or uranium, and then try to, by a better understanding of the interaction with soil matrices and other matrices of environmental interest, to be able at the end to predict and to obtain more robust KD values. So among these four subtasks, the work presented here is related to the task 4, at 2.7.4, which aim at developing models in order to predict such a specific KD data, and with two different approaches. So those two different approaches have been summarized in a recently finished deliverable, 2.17, and with two different sections, one dealing with an approach based on parametric models and distribution functions to predict KD, which is roughly the task of the University of Barcelona, and then the second part, which is developing the smart KD based approach in order to, based on the description of the chemical reactions between norm and solid and liquid phases, to be able to predict KD. And this is the second part of the talk that Victor will give you if he's alive and kicking. Focusing in our part, I mean, just two slides to share with you the overall approach. And for one side, we detected that there were data gaps on KD, maybe not so many for uranium, but for sure for radium and polonium. So we decided to carry out a number of experiments in order to obtain sorption and disruption KD values with a nice soil collection that we have with more than 30 soils, well characterized with a number of interesting soil properties. And then we carry out sorption and desorption experiments in order to obtain sorption and desorption KDs using radium-226, polonium-210, and uranium-233. And we weren't satisfied only for having this kind of own data set, but we wanted to extend our data set, gathering data from the literature in order to complete the range of soil properties covering by those different KDs values. So this is what's described in a milestone and another deliverable, which are accessible in Barcelona web, but just to put it in context. So at the end of the day, we have a data set with this kind of two contributions, all experiments carried out within Redolon project and data gathered from the literature. And for every single KD entry, we may label this entry according to the source, according to the soil properties, such as, I don't know, pH, organic matter, texture, CEC, status of the measured cations, both in the changeable complex or in the soil solution of the soil, carbonate, dissolved organic carbon, dissolved inorganic carbon, specific surface area, and so on. And then also we have tagged every KD according to the methodology, either sorption KD or dissorption KD, or even when the data came from native radionuclides, so it's called long-term KD, in order to distinguish those populations. And from this data set, we are ready to play statistical analysis in order to be able to derive predictive KD models. So, just to have an idea, mainly we have applied typical statistical analysis like principal component analysis and partial least square regression in order to explore which are those relevant sort properties affecting KD values, affecting KD variability. And then once those sort properties were properly identified, we followed two different tracks. The first track is we have enough characterization data from those entries in order to play the game of creating parametric equations. If the answer is yes, let's go for it. And then we construct parametric models, univariate or multivariate, we'll see a couple of examples of that, in order to predict KD based on those parametric equations. When the scenario was a little bit exciting because we didn't have enough characterization data, a second approach was to construct probabilistic functions in order to compare different populations of KD, and from that to be able to derive best estimate of a soils group according to a relevant property, and then from the 50% percentile, we have a best estimate, which always is going to be a better approach than using a single overall KD for a single radionuclide, regardless of the properties of the soil. So those are the two, and I'm going to put some examples of every scenario. Let's start by radium, focusing only on sorption KD of radium. From the PCA, we selected a number of variables to be candidates for those parametric equations, and from the PCA, we carry out a PLS analysis, and just as a summary, as an example, we consider the VIP score, the variable importance in projection score, as a nice index to try to identify those variables to be tested for the construction of parametric equations. As those people knowing a lot about PLS, the threshold of 1 is the one recommended for such selection. So those variables having a score, a VIP score over 1, were those tested for parametric equations. And for the specifics of radium, it was shown that calcium plus magnesium status, both regarding exchangeable calcium magnesium and water-soluble calcium magnesium status, and then converting those data into a KD of calcium plus magnesium. So this kind of calcium plus magnesium status was converted into a KD of calcium plus magnesium, was a nice variable to be tested, along with pH, along with surface-specific area, along with manganese status of the soil as well. And from this, first of all, we tested a univariate linear regression, and nicely was shown that those are data with standard data sets, that we could be predicting the KD of radium basic only on calcium and magnesium status. So it's a simple equation in which we may describe more than 75% of variability of KD. So quite nice to have a simple equation in order to predict KD. If we have more data, we can get a more complicated equation, and then the variability described of KD increases just a little bit up to 82. But in that case, besides calcium and magnesium status for the KD of calcium magnesium, we add pH, we add specific surface area, manganese status. But going beyond the typical characterization of the soil, we may have very nice parametric equations to predict KD in the case of radium. I'm going to use radium again in order to illustrate a case of CDFs, of probabilistic functions. In that case, for instance, we compare the populations of sorption KD, dissorption KD, and long-term KD. And those are different populations, statistically speaking. We may see that the sorption population is statistically different. The central best estimate value derived from the percentile 50 is leading to a much lower, can be around 870 with respect to the other KDs of the other two populations. So from that point, no longer we have to mix up the social and social KD, we have to distinguish those scenarios to have a better estimation of the KD. And even, for instance, taken as an example, the social population, for a regular parameter that always is mentioned, always is informed, like pH, we can make a step further and say, okay, let's distinguish between acidic soils from non-acidic soils. And at least we may get KDs differing in one order of magnitude, which sometimes makes the difference in risk assessments. So we may say that for sunshine KD with acidic soils, the KD is going to be much lower than a KD from gradient for alkaline soil. This is a simple example of a scenario in which we only have pH information in my KD entry. So another example will be polonium. In that case, the VIP score indicates that there are different variables that should be taken into account. Again, the surface specific area, calcium, magnesium, the status of the major cations in the exchange complex, the soft organic carbon or the solid organic matter, texture, and the soft inorganic carbon. And then again, we can construct parametric equations, and we may see the main role of a specific surface area that sometimes, as a surrogate, some people may indicate the clay and silt content of the texture and fraction of the soil. But actually, the variable which makes the difference is the specific surface area. And then if we have more information, like the status of monovalent cations, the status of the soft organic carbon, and so, then we can go up at nearly 90% of the probability of KD, of the sorption KD of polonium can be predicted in the soil. So again, if 1 minute left. Okay, well, so let's go to uranium. Let's go. I'm sorry.
For 12 minutes, so I don't know how much Viktor will talk.
Okay, so I'm going to uranium.
No, we told me 40 minutes.
I'm going to uranium just to say that for the first time we have a single equation covering all the pH for uranium, which is just a nice output for our project. So for the first time, we no longer divide the KD uranium prediction according to pH ranges. We may have a single equation for the whole of the range. You know this well-known, well-shaped relationship between KD and pH, and then we have this equation that also can be optimized and improved by including other variables up to more than 80%. So just take-home messages. I think Radon has produced a step forward in the prediction of KD of those radionuclides of radium, polonium, and uranium, because for the first time we have parametric equation able to predict KD. Then end user must select the equation according to the information which is available, but please no longer stay comfortable with organic matter and pH. We should be acknowledging the role of the soil variables, and then must be characterized. And when we don't have so many soil characteristics, there's a second best option, which are based on comparing populations and grouping soils based on relevant properties, maybe not so significant, but relevant enough to be able to derive best estimate KD, which are more representativity than the single overall KD for a target radionuclide. So, Viktor, I give the floor to you if you are there.
I'm here, yeah, thank you.
Great. So
thank you, Miguel. Yeah, I think in.
No, it's the same presentation.
And I can.
Yeah. It's the same presentation, right?
It's the same file.
Yeah, the same file.
Unless Viktor want to share himself.
I can share my screens, no problem.
Yeah, but it was all there, so
well, so he can share it.
Can you see my screen?
Yes.
Perfect. Okay. Sorry. Yeah. Okay. Then, since with the time, I will just start right away. I'm presenting the results from the HZDR part, and here we go. Okay. So, what is just a small thing is like the smart KD approach is so. The so-called smart KD concept calculates Knorr sorption processes in natural systems using thermodynamic models. Thus, the smart KD values are mainly based on mechanistic surface complexation models and ion exchange. So sorption is described by the component additivity approach, in which the contribution of the sorption of one Knorr is considered on every single mineral of fraction of a sediment, also including relevant competitive effects. The distribution coefficient may vary depending on the actual geochemical conditions, but this can be included into the KD calculation. The Roffon site is a former uranium mine in France and was chosen as the test site. Within the whitish layer in the downstream below the tailing, higher node concentrations were found. And the chemical and the mineralogical description of this layer was delivered by Gilles Montalvon et al., and it was used for this KD modeling. A thermodynamic model was set up as also taken into account the sorption of competition using ubiquitous ion in nature, like calcium, magnesium, aluminum. And unfortunately, for many sorption reactions of an ion onto specific minerals, no thermodynamic models are available in literature, and here chemical analogs were applied. For all surface complexation models, some normalization procedures had to be applied to obtain consistent surface complexation model dataset. Some information like minerals specific surface area, for instance, had to be estimated from literature, and a PSI database was used for calculate the aqueous chemistry as well as the mineral solubility. For the uranium, a large variety of KD could be obtained when calculating a KD under varying geochemical conditions. This is due to the effect of uranium redox chemistry as well as carbonado and earth alkaline carbonado complexation at neutral pH values. And at exact Roffon site conditions, the calculated KD matches very good with the KD values measured from the field samplings. Also for radium and lead, KD values could be obtained. Here, major data gaps in SEM data, as well as missing information on sorption and barium concentrations in the system to calculate radium containing soil solutions are sources of uncertainty. And here I want to show you some results of batch sorption studies from barium and strontium on gibbsite as chemical analogs for radium. What you see here is the sorption curve of strontium on gibbsite, with the concentration of sorption is 10⁻⁶, solid to liquid ratio is 0.5, and the background electrolyte is sodium chloride. It's 0.01. So you see the sorption starts at, wait, can I? Here. The sorption starts at pH 9 and reaches its maximum at pH 11.5. And when we increase the background electrolyte by 10, we see the sorption curves shifts to a higher pH, so it starts at roughly pH 11. And then we change the conditions of the systems, like changing the concentration. Here we increase the concentration a bit, so we change the slope. We go back to 10⁻⁶ and change the solid to liquid ratio. We see the shift here. And even here, we change both concentration and solid to liquid ratio. And this systematic change of parameters was also applied to barium system, and you see those systems are very similar. And the biggest information here is from the black and the red points. We have this big data gap, which is giving us the indication of having an autosphere complex forming on the surface of gibbsite. We also measured the zeta potential of the pure gibbsite, which are the black and yellowish points here, with two different background electrolytes, and we see there is no shift of the isoelectric point, which is at pH 8.1 here. But when we apply also the sorptive, we see an increase of the surface charge. So after the surface of the gibbsite is negative, so we also have an indication for having an autosphere complexation here. The same for barium as well. When we keep the pH stable and change just the concentration, at higher concentrations here, we see we reach a plateau, which is because of saturation of surface sites. And at lower concentrations, we have this linear increasing sorption here. And this linearity is giving us the information that we have only one species which is present on the surface of the mineral gibbsite. Since the conventional spectroscopic methods are not useful for earth alkaline metals, we used EXAFs and for strontium and for barium on gibbsite. For barium, it didn't work out that well because we had issues with focusing the laser in the right wavelengths. Sorry. But since we have this high similarity here for barium and strontium, we can also just take a look on strontium. And from the paper Pappalardo et al., we know those guys here, they investigated into the hydroxide shell of strontium, and we know those numbers matching with our numbers which we got from EXAFs here. So we know this distance here is related to strontium to oxygen and not to strontium to aluminium, for instance. So this is also an indication for an autosphere complex which is forming. Here we have the modeling. So all the data we got, all the information we got, we tried to bring into a model. And the first rows here are about surface properties, but what I want to bring your attention to the last two rows here. We have a fitting with FitQL and with FreakC, and the log K values are very similar here. What you see here is fit with FreakC, and you see the most curves are very close to the points. The only curve is the blue one here, which is far away from the points. So this needs to be improved. But we are working on this with titrations. We want to get better surface properties numbers, and so we improved the modeling. So our conclusion and take-home messages is we have improved prediction. The improved predictions are possible. New sorption data on modeling approaches enhance the prediction of KD values for earth alkaline metals like strontium barium on aluminium hydroxide. Good field data is crucial. Without comprehensive and standardized field data like mineralogy, etc., uncertainties in modeling persist, and mechanistic thermodynamic models are very well suited to calculate the KDs for specific geochemical systems. Just to give you a small outlook, like I already mentioned, I'm working on optimizing the suffix complexation model for the systems strontium and barium on Gibbsite. And I also have I'm finishing the experiments with radium. Those are ongoing and running at the moment. And also I want to do the surface complexation modeling and discuss the analogy between those three systems afterwards. I want to acknowledge Joan from Universitat de Barcelona, Andre, Salim, Marine, and Sabrina, which helped me with this project, and it was always nice to work with. And yeah, that's it. Thank you.